get just the Bratteli diagram without an order. And remember that this diagram is given by a, this is something like this. Okay, and here we have some matrices. So we have these sets of vertices Vn and the incident matrices An. So when we have this, we can see the following. So suppose that I'm going to start from C V0. Then I'm going to put here Z, the number of elements in V1. Same thing here for V2. And like this. And if you see, the matrices An define homomorphism from, for example, here I put A0, here I put A1, and so on. So we have a limit like this. And what can we do when we have this? Here I just wrote something, but I didn't define anything. So every time that we have something like this, we can define a limit. I don't know if you are familiar with direct limit. So what is a direct limit? It's if you want, for example, suppose that here you have always the same group, and here you have the identity, or suppose that you have an increasing sequence of groups, and here you have an inclusion map. So the direct limit will be something like the union. But when you don't have this situation, you can define something similar. So to define the direct limit, we are going to identify points which arrive to the same place. So we are going to say, okay, first I'm going to define the set of all the pairs Vn, where V is in Z Vn. This is just a set. And then I'm going to define a relation here. I'm going to say, okay, Vn okay, we are going to say that the pair Vn is equivalent to Um if and only if for some k bigger than n and m, when we apply the transformations to V and U in the step k, we arrive to the same place. This is the relation. So we identify pairs like this. And we take G, the quotient for this relation. We are going to write this element like this. And in this set, you have a group structure. So the same group structure that you have in the product can be defined here. So this is a group. I don't know, for example, this is just to say, okay, if we are not in the same level, we can't just say V plus U, but we go to some K bigger than N and M, and we just write like this. And this is the direct limit of this sequence. The plus here is just the plus in C, B, K plus 1. This is the plus. Okay, so this is a group. And there is another thing that we can see here. The matrices are always positive, because are the incident matrices of a Bratteli diagram. So all the positive elements, for example, in CV0 goes to positive element here, and every positive element here goes to positive element here. So we can now define something which is a positive cone. So if you go to the definition there, in the definition there we define an ordered group as a pair G, G plus, where G plus is a subset of the group, verifying the three properties, the three first properties there. So in that case, we can do the same. Here, the positive cone, G plus will be just the equivalent classes of the positive elements, or the non-negative element, if you prefer. This is a subset of G. And if we take the pair G, G plus, we say that this is the dimension group associated to the Bratteli diagram. And all these objects come from C-star algebras and K-theory. So the notation that we use here we call, okay, I don't know, we call this the K0 group of the Bratteli diagram. So if you see this, this means G and G plus, constructed like this. And there is a theorem from Hendelman, Efros, and Shen. This is from 81. That says that every dimension group defined like this, using a Bratteli diagram, is exactly an object like I defined there, and vice versa. So dimension groups are these objects or the objects which are defined there. This is an abstract way to define a dimension group, and this is a way to define a dimension group using a Bratteli diagram. And the dimension group is called simple if you are using a Bratteli diagram which is simple. So simple means that the matrices are strictly positive, or if you can contract the diagram in order that the matrices are positive, strictly positive. So simple dimension groups are exactly this object produced from simple Bratteli diagrams. Okay. And why we are defining this, what is the relation with this and the minimal Cantor system? So yesterday we saw that for every Bratteli diagram, if we put some order, we get a minimal Cantor system. So the question is, okay, what happens if I have a minimal Cantor system? I take a Bratteli diagram that defines this minimal Cantor system. What kind of properties can tell the dimension group of the Bratteli diagram associated to this system? And also maybe the first question is to know what happens if I have a minimal Cantor system. I have two different Bratteli-Verchick representations, and it's true if the dimension groups are the same or not. So maybe this is the basic question. And in fact, the dimension group does not depend on the Bratteli diagram that we take to define a minimal Cantor system. And for that, we need to see the following. Now, suppose that we have a minimal Cantor system. So this is something for Bratteli diagrams. And now I'm going to define the same thing for minimal Cantor system, but in a different way. Now, suppose that we have a minimal Cantor system. And then from this system, we are going to define a group, an ordered group, as the group which is written there. So what can we do here? We are going to take G as the set of continuous function from x to the integers, and this is an abelian group if the operation that you use is just the addition, countable abelian group. And we are going to take something related with the dynamic. This is independent on the dynamic here. But now I'm going to take a subgroup of this that we are going to write like this. And this will be the subset of all the functions here that can be written like this. These are called the co-boundaries functions. And this is a subgroup of this bigger group. And this subgroup depends on the dynamics, depends on T. And we are going to take, okay, this is not G, sorry. We're going to take just this group, then we take this subgroup which depend on the dynamic, and then we are going to define G as the quotient of this group of the continuous function from Ex to Z by the subgroup of the co-boundaries. And we are going to identify, we are going to call G plus the equivalent classes of the non-negative functions. And we can prove, this is all the things that I'm going to talk today, they are all also in Hermann Putman scale. I forget to say this. And we can prove that this object is an ordered group. Verify the properties 1, 2, 3 written there. And then the question is, okay, I know that this system, this minimal Cantor system, can be represented using a Bratteli diagram. So the question is, can I, in some way, relate this order group with the dimension group associated to the Bratteli diagram of this minimal Cantor system? And the answer is yes, they are isomorphic. Isomorphism here means that a group isomorphism that send the positive part to the positive part, and some element that we call the unit to the unit. So I'm going to say this now. So now suppose that we have a Bratteli diagram. A Bratteli diagram, an ordered Bratteli diagram that define this minimal Cantor system. So that means that the minimal Cantor system that we read in the Bratteli diagram is conjugate to the minimal Cantor system that we took at the beginning, xt. What is the relation between the dimension group defined from B with this ordered group that we defined from the system? And so the answer is that they are isomorphic. This dimension group is written, is called using the same terminology like K0 xt. So the theorem says that K0 xt is isomorphic to the Bratteli diagram, to the K0 group, the dimension group given by the Bratteli diagram. So both things are isomorphic. And how can we define the isomorphism? So the way to define this isomorphism is the following. So for one side, we have this group. And here we have the direct limit given by this sequence. So we have to find something that pick an element here and send an element in this part. And the way to produce an isomorphism between both groups is, for example, here. There is another thing that I didn't tell you that I'm assuming here. First, it's very easy to show if you have two minimal Cantor systems, x1, t1, x2, t2, if they are conjugate, these groups are isomorphic. So if I know that xt is conjugate to xb, tb, so the dimension group K0, xb, tb will be isomorphic to K0 xt. So we can assume that, in fact, that we need to show here is this. This is that we have to show. And for that, the function here that we can define is, okay, I'm going to define the function that, okay, remember that this system, xb, will be the set of infinite paths in B. And in xb, I can define cylinder sets. For example, I see the cylinder set of length n. And that means all the cylinder sets which are defined by the path that arrive to Vn. And I can just, okay, if I see all the paths that are arriving to the same vertex, all the paths which arrive to the same vertex, if I take the index function on this cylinder set, they are equivalent by this, they are in the same equivalence class. So I'm going to say, okay, I'm going to take the class of the index map on the cylinder set that fix the minimal path arriving to the vertex V in Vn. Suppose that the vertex V is, I don't know, this is the, okay, the vertex V. And I'm going to send this to the class of the vector the unitary vector in Cvn in the coordinate corresponding to the vertex V. If I define this, this will give you the isomorphism that we are looking for. Okay, so because the dimension group, defined by the minimal for the minimal Cantor system is isomorphic to the dimension group given by a Bratteli diagram that represents this minimal Cantor system, and this is independent on the Bratteli diagram that we are using, we can say that this is the dimension group associated to the minimal Cantor system. So every time that we have a minimal Cantor system, we can take any representation in terms of Bratteli diagram for this system, and the K0 group for this Bratteli diagram is the dimension group of the minimal Cantor system. So we just need to think about Bratteli diagrams. And if we want, we can forget this representation of the dimension group, if we want. So this is the first thing. So the dimension group, K0b, will be the dimension group for xt, and this is for any Bratteli diagram that represent the minimal Cantor system. And now there is something that I didn't tell you, but when we define the dimension group, when we see the Bratteli diagram, we are not using the dynamic here. The dynamic is given by the order. And when we define the dimension group, we're just using the picture. So one question is to know, okay, what happens, for example, if I take two minimal Cantor systems having the same dimension group? what can we say about these two minimal Cantor systems? And if we are not using the order in the Bratteli diagram to define the dimension group, it's more or less clear that maybe they are not necessarily conjugate, but there are some way to relate these systems. And the way to relate this system is just the notion of orbit equivalence that maybe you have that you have seen during this week. And okay. So before to say something about that, I would like to show, okay. Some properties that we can see from the Bratteli diagram. So there is one property of the minimal Cantor system which is very easy to see from the Bratteli diagram. So suppose that we have a minimal Cantor system with a K0 group given by some Bratteli diagram. And one property that we can see in a very easy way from the Bratteli diagram is the set of invariant measures, the set of invariant probability measures. What is the set of invariant probability measures? Okay, are all the Borel probability measures. Which are invariant with respect to T. And this set can be described from this group. And how can we describe this set from this group? In this group, there is something which is called a trace or a state. Of a dimension group or I forgot to say something, sorry. When we speak about dimension group of a minimal Cantor system, we talk about the group, the positive cone, and we need to fix an element. And this element will allow to normalize, in some sense, the measures. And what is the element that we fix? I'm going to write this here. We take the dimension group. We take the positive cone. These are just the classes of the positive, the non-negative element. And we fix the class of the first vertex in the diagram. So remember that the diagram always starts with C here. And here we have the matrix A0. And here we are just writing the class of the element 1 here. And when we see this in this representation of the dimension group, this corresponds to the class of the function of the constant function equal to 1. So when we define this isomorphism will send the constant function equal to 1 to the class of the element 1 in Z. So this isomorphism sends the group to the group, the positive cone to the positive cone, the class of the constant function 1 here to the class of the element 1 in Z. And this is very important. We have to find an isomorphism that sends positive cone to positive cone, unit to unit. So when we have this, a trace or a state of a dimension group with unit, will be a homomorphism from the group G to the reals such that the positive cone goes to the positive reals and the unit goes to 1. This is a state or a trace of the dimension group. And what happened with the space of traces here in this dimension group? The space of traces of the dimension group for a minimal Cantor system coincide or is affine, or there is an affine bijection between this set and the set of invariant probability measures. So the set of invariant, there is an affine bijection between the set of invariant probability measures of xt and the set of states that I'm going to just write like this, of K0 of this. So these two things are the same. And what is the way to define this correspondence? So we take a measure here, and we just define the function. And here I'm going to use this representation, maybe. We just define the function that take a class here and give you the integral of this function with respect to the measure. And this is the way to relate both spaces. So the dimension group has a space of state. And this space of state, we can think of this like the set of invariant probability measures of the minimal Cantor system. And here we can, the first thing that we can say, if we see this, is, okay, if I have a minimal Cantor system which is uniquely ergodic, for example, and if I have another system, we have two ergodic measures, so they can't have the same dimension groups. So this is a first way to try to classify system using the dimension group. But the problem is that there are infinitely many dimension groups which are not isomorphic, but with just only one trace. So there are a lot of minimal Cantor systems which are uniquely ergodic, but different dimension groups. So the dimension group defines something which is more strong than say that the system have the same set of measures. And the property, which is a complete invariant for the dimension group, is something which is called strong orbit equivalence. And for that, I'm going to define first what is orbit equivalence. Suppose that we have two minimal Cantor systems. We can define this for more general group actions. Today I'm going to work just with C actions, and tomorrow we are going to see something different. So suppose that we have two minimal Cantor systems. We say that these systems are orbit equivalent if there is an homomorphism from one space to the other space, that send the orbit of one system to the orbit of the other one. This is the topological notion of orbit equivalence. And maybe this was defined here before, but when we have a map like this, we can define another function. We can define two more functions. We are going to say alpha from x to the integers and alpha from x1, if I'm using the notation there. Alpha will be the function that picks some x and give you alpha x, where alpha x is the integer we're satisfying this. So we have the orbits here. This is the orbit of x. This is the orbit of hx. In the second system, we know that this orbit goes to this orbit, but we don't know which is the order. So here we have T1x. And this T1x will go somewhere here. And this is the point which is called alpha x. This is T2 alpha x hx. And we can do the same, but to the other side. And this is the function beta from x1 to c that sends x to beta x, where this beta is given by this relation. So here we have SHX, and we know that this comes from somewhere here. And this is T1 beta XX. So we have these two functions. And the notion, this notion is a little artificial, but this notion will give you the complete invariant for this K0 group. There is a stronger notion for orbit equivalence. We say that sorry, yes, this is T2, yes, sorry. And here the same. Okay, we say that those systems are strong orbit equivalent if they are orbit equivalent and are strong orbit equivalent if they are orbit equivalent, and if this is the function that gives you the orbit equivalence, if they are orbit equivalent, and if the function, if they are orbit equivalent, and if alpha, the function alpha and beta have at most one point of discontinuity. So this is an orbit equivalent, but in a very ordered way. H? Yes. Homeo. Yes, it's an homeomorphism. And the relation between orbit equivalence or strong orbit equivalence and dimension group is the following. This was shown by Giordano, Putman, Scow. In 95. And the systems are orbit equivalent, strong orbit equivalent. If and only if the dimension groups are isomorphic. Has dimension group with unit. So the dimension group will give you a complete invariant for this property, for strong orbit equivalent. How can we prove this? The proof of this result used just the combinatory of Bratteli diagram. And maybe something that we have to see is that two Bratteli diagrams have the same dimension group. If and only if there is a third Bratteli diagram, such that if you telescope the Bratteli diagram to the odd level, you get B, and if you telescope to the even level to the Bratteli diagram, you get B prime. There is always a third Bratteli diagram. This will allow you to show this result. But the question is, okay, this is true for strong orbit equivalence, but what happened with orbit equivalence, which is the natural notion, if you want. And, okay, to get some invariant for orbit equivalence, we need to take the dimension group and make a quotient for a subgroup. Yeah, if the system are not strong orbit equivalent, yes, you have more points of discontinuity. If alpha and beta are continuous, and this is a result from Mike Boyle, if alpha and beta are continuous, this is equivalent to be flip conjugate. So if alpha and beta are continuous, the systems are flip conjugate. So that means that T1 is conjugate to T2 or T2 minus 1. But you can have this intermediate situation. So if there is only one point of discontinuity, you are in the strong orbit equivalent situation. And if you have more points of discontinuity, okay, I'm going to show you what happened to be an orbit equivalence. You are orbit equivalent, but maybe not strong orbit equivalent. Okay, so to have a complete invariant for orbit equivalence, we need to take a quotient of the dimension group. Now suppose that you have a dimension group with unit. The infinitesimal subgroup of the dimension group will be the subgroup of all the elements with the property that if you apply some trace to this element, this always gives you 0. And in the case of the dimension group for minimal Cantor system, okay, and then you can get another dimension group, which is the dimension group quotient by the traces. And here you take the class of the unit. This is another dimension group, simple dimension group. And in the case of the minimal Cantor system, this is equivalent to take the set of continuous functions to the integers and make the quotient with the functions having 0 integral with respect to any measure. This group, in terms of the minimal Cantor system, is isomorphic to take this. For some systems, for example, there are dimension groups with trivial infinitesimals, and in that case, this group is the same, the first one. And the invariant for orbit equivalence is this group, the dimension group quotient by the infinitesimal. And this is a more complicated result. Sorry?
If I take it, I can always write.
Okay.
Bigger. What I'm saying is that.
They are always like this? Or no?
Well, I think it's just that.
But sometimes this set coincides with the coboundary for some cases. For the coboundaries with integer values for some cases. And the theorem, this is also Giordano-Putman-Scout. So the systems are orbit equivalent. If and only if the dimension group quotient by the infinitesimals are isomorphic as dimension group with unit. Okay. And how much time I have? 5 minutes. Yeah, just to say some little comments. For example, for systems that we know, what happened for the odometer, for example? Suppose that we take the odometer in base the odometer given by base Pn to power n. The Bratteli diagram that can we use to describe this odometer is a Bratteli diagram having just one vertex at each level and two edges from one level to the next one. So the dimension group is given by this. This is the dimension group of the odometer in base 2 power n. And you can show that this is isomorphic to the dyadic numbers. And the positive part is just the intersection of this with R plus, and the unit is 1. Can you prove that? Okay, the only trace here is the identity. So you have to take an homomorphism that sends the dyadic numbers to the real and the positive part to R plus and 1 to 1. So you don't have too much. So it's the identity. And in fact, here the infinitesimals are also trivial. So this is uniquely ergodic. The infinitesimals are trivial. So in that case, orbit equivalence means, okay, the group quotient by the infinitesimal is the same group without the quotient. And another example, which is similar, it's uniquely ergodic too. I don't know, I didn't talk about Sturmian systems, but okay, in a Sturmian system, you have to take a rotation alpha in the circle, an irrational rotation, and then you take a partition, the partition 0, 1 minus alpha, 1 minus alpha 1, and you start to codify the orbit using this. And then you take the closure of this codification in 0, 1, z, and you get a subshift. This is the Sturmian subshift for alpha. And for this thing, for this subshift, you can, okay, there is a Bratteli representation which is given by this. Where A1, A2 is the continued fraction representation of alpha. And in that case, the dimension group that you get is Z plus alpha Z. The positive cone is this intersected with the positive reals. And the unit is 1. So this is another case of a uniquely ergodic system, and the groups are very different. So the group of the odometer and this group. So these are not strong. These are not orbit equivalent. Just a last comment. What can we say for more general group actions? Okay, Maybe the problem with Bratteli diagrams is that they are very useful for C action, but if you want to work with more general group action, there is no way to define a Bratteli diagram. But if you work with partitions, remember that Bratteli diagram comes from Kakutani-Rocklin partitions. When you work with partition, maybe you can do something similar than for C action. And there is an extension of this result for CD action. And the extension says, this is from Giordano, Matui, Putnam, and Scow. This is from 2010. And they show that two systems given by, for example, one minimal Cantor system given by a CN action and the other one given by a CD action are orbit equivalent if and only if the group given as I defined before, like this, if and only if these groups are isomorphic. Okay, so the equivalent classes of the CD action and the system have to be minimal and free. So the orbit equivalent classes for minimal free CD actions are also described by these dimension groups. And there is a consequence for this. So in fact, they show that, okay, this object, they always comes from Bratteli diagrams. So they are also simple dimension groups. So a consequence for this result is that every minimal free CD action on the Cantor set is orbit equivalent to a minimal C action on the Cantor set. Because for every simple dimension group, there is a minimal C action. And here we are saying that if we pick a Cn free minimal action on the Cantor set, this action will be orbit equivalent to any other action having this dimension group.
What is TI?
Mm-hmm.
What is TI?
This is the name of this action, and this is the name of this other action. They are, okay, or this is not important. Maybe just think this is a CN